All right. So I wanted to make a quick recording. I feel like we had to go very quickly at the end there. And of course, it's Friday morning. So maybe I could have done a better job of timing things out so that you could see about the connection between electric field and potential. So hopefully, this is just sort of the extra 10 minutes that I didn't quite have today to look at that. When we want to make a connection between field and potential, most of the time we have the electric potential and we want to use it to find the electric field. And like I mentioned, because we know that the way that we calculated the potential was by finding the work done moving a charge from one point to another. So we had to do an integral over a displacement. Then the mathematics that we need for finding the electric field from the electric potential is the derivative. So when the potential is a known function of position, the electric field is found with two steps known as finding the gradient. And this is the more general way when we're thinking about a two or a three-dimensional system. And what we need to do is we need to find the direction, which is the direction of steepest descent. And we need to find the magnitude. And the magnitude is the rate of change of potential with respect to location, or the derivative, essentially, of the potential with respect to position. This connects exactly to what we did when we were drawing the fields. We know that when the field is strong, when the value of E is large, that's when the potential lines are close together. They're changing quickly. In this picture to the right, in this picture to the left, we have the field line, or the potential lines are close together near the positive charge and near the negative charge. And so those are going to be the regions where the magnitude of the electric field is largest. Over here, where the electric field line, or where the electric potential lines are far apart, then the electric field will be weaker. Here, it doesn't really even matter what the values of the potential are. It just matters how quickly the potential is changing. So if we were going to need to do this quantitatively, we would need to know a distance scale on this figure, and we would also need to know what the values of the potential were. So if these are separated by, say, 1 volt, and this is 0, this might be 0, +1, +2, 3, 4, 5, 6, 7, and this would be maybe -1, -2, -3, 4, 5, 6, 7, etc. And so then you could find the strength of the electric field by saying between 0 and -1, there's, say, a centimeter of distance. And that would be um, an electric field strength of 1 volt divided by a distance of 0.01 meters, or 100 volts per meter, which is the same thing as 100 newtons per coulomb. On the other hand, over here, that change in 1 volt would be over maybe a quarter of a centimeter, a millimeter, something like that, and the value would be larger. The second thing is finding the direction of steepest descent, which will be perpendicular to the potential, the equipotentials at that point. And notice what we mean by steepest descent is how do you go across the potential lines most quickly? So you'll notice that this arrow here goes down across the potential lines as quickly as possible, staying just perpendicular to them. There's a lot of different arrows that are this same length at this point. This is the one that actually gets you across the nearest potential line. So you're trying to point downhill, and that's how you would find the direction. So you can find the magnitude by looking at the difference in potential and the separation of the lines, and the direction by finding the direction of steepest descent. In a one-dimensional graph, the one we had a chance to talk about, this is obviously much easier because you don't have to worry about the direction of steepest descent. You're just looking downhill for the direction. It's either to the left or to the right. So here, where the potential is decreasing as you get closer and closer to zero, the electric field in this case, it's a gravitational field, but the gravitational field clearly points towards the origin. So from 12 to 0 here. The magnitude can be found as the gradient, which in this case is the slope. Here's a tangent line. Here's a line that's tangent to the curve at a distance of 4 million meters. You can find the slope of it. It goes from 0 down to negative 25 over about 8 million meters. So you can just do the negative 25 times 10 to the ninth joules per kilogram divided by that distance, and you'll have then the field strength, and it points to the left. Right? So those are actually pretty easy to do. You just have to find the slope of the tangent line. The capacitor is a nice, easy situation to analyze. So here's a problem that we can do, and I should be able to talk through most of this. With the capacitor, remember the plate separation is here. The electric field is approximately constant in the middle, and the equipotentials are lines that are parallel to the surface of the plate. And so here it's saying that the capacitor, that we have a distance of 0.1 centimeters or 1 millimeter. The top plate is at 50 volts. The bottom plate is at negative 50 volts. What is the electric field strength? Well, the electric field strength is the rate of change of the potential. So we go over 100 volts in 0.1 centimeters. So you would do 100 divided by 1/1000th, and this would be 100,000 volts per meter, which is the same thing as 100,000 newtons per coulomb. So that's the strength of the electric field. A general expression for the electric field, if you knew what the difference in potential was and what the separation would be the change in potential divided by d, the distance between the plates. And then, of course, what's the direction? Well, it points from positive to negative. The last question, an electron is released in the middle. Describe its motion. Well, the force that acts on the electron will be Q times E, which is negative 1.6 times 10 to the negative 19th times the electric field, which was 100,000 newtons per coulomb. So multiplying 100,000 or 10 to the fifth times 1.6 times 10 to the negative 19 would give you a force of 1.6 times 10 to the negative 14. The negative sign means that the field points down, so the force points upwards, which is not a surprise because the negative plate will repel and the positive plate will attract the electron. And so that force that is large relative to the mass of the electron will accelerate it towards the positive plate. And if you had the mass of an electron, you could actually figure out what that acceleration is, dividing by the mass. So that's sort of a typical potential question that ends up relating to the electric field. And the last thing that I wanted to show you is this is where we really see the electric potential's advantage. Because the potential is a scalar, it's very, very easy to sum contributions from many different sources. And once you're comfortable with calculus, finding a gradient is just a mathematical operation. And so rather than doing the vector work of adding the vectors of the electric field that you can calculate, you can do the very simple scalar mathematics of adding up potentials and then the math of taking a gradient. So I want to just show you here a Desmos that I put together. The idea here is that there are 3 charges that are on the x-axis. There's a positive charge of 2 coulombs that's located at the origin. So we see its potential here that is positive and peaked at the origin. There's a negative charge of negative 3 coulombs that's located 5 meters to the left. And there's a positive charge of 4 coulombs that's located at this position of 8. And so the question that and then to scale things, this sort of arbitrary units, I'm going to set the value of k equal to 1. And so we see the individual potentials here, but then finding the total electric potential is very easy. I just add those numbers together. And so taking away the individual potentials, we see now the potential of all of those. You can see the features of the individual charges and then the sum of them. Then, if we wanted to, it's pretty easy to find the gradient. You can open up this menu if you want and take a look at it. But here I'm just finding what the gradient is, what the slope of this is. And the slope will be equal to the strength of the electric field. And the electric field points downhill. It points in the direction of steepest descent. So as we move along this curve, we see the slope, we see the gradient, and it tells us what the magnitude of the field is, where the field is strongest, that's where the curve is steepest. Where the slope is positive, that means that the field points to the left or downhill. Where the slope is negative, it points to the right. So those signs are a little bit different than you might expect, right? Because it points downhill. One other thing, and we brought this up earlier, and I mentioned it, was there was a connection between where the slope is equal to 0, and of course, where you have those minima along the potential, those are the places where the slope is 0. Since we now know that the slope is the electric field, these are the places where the electric field is 0. So working with the potential and the gradient is often an easier way to figure out where the electric field is 0. And of course, because it's calculus and you have a function here, you don't need to do anything numeric or tricky to find the slope. You can actually just take the derivative of that potential. And when you take the derivative of the potential, you can get the strength of the electric field. And remember, positive values point to the right, and negative values point to the left, as long as you put a negative sign here in front of the derivative. So now, to find the electric field at all points in space, instead of doing a vector sum of the 3 different vector fields from these 3 different points, I've done just a scalar addition of the 3 different scalar behaviors, and then I've taken a derivative. And now I have the strength and the direction of the electric field everywhere. So that's one reason to use potential. I hope this is helpful to you. Take care.